All right, let's begin. So I have a simple data frame that I am creating. Today's session is going to focus on causal inference, the topics that have been covered in class already. So I have a particular set of IDs for people ranging from 1 till 5. Then I have T, which basically just tells me it's a function that tells me if I have assigned a person to the treatment group or to the control group. From this data, we can see that 3 out of 5 people were administered the treatment to. Then I have the outcome with the treatment. That's basically yi of 1. And then I have the outcome without the treatment, yi of 0. We're going to try and find the Basically, we're going to try and find the average treatment effect first and then estimate it. Yes, Mohit, go on.
मैंने आपसे पूछना था कि एक कंफ्यूजन मुझे लेक्चर में भी थी कि जिन लोगों को ट्रीटमेंट एडमिनिस्टर नहीं की हुई उनकी आउटकम में ट्रीटमेंट कैसे हो सकती है हमारे पास।
That's a wonderful question. The thing is, उनकी outcome हमारे पास नहीं है. This is a hypothetical scenario. In actual, let me tell you what values are missing. I have no idea what this value should actually be. And I have no idea what this value is, and what this one is, and what this one is, as well as this one, 0.3. Because for this particular person with the ID 3, for instance, the treatment was administered. So I know about the outcome when the treatment was administered, that's 0.7. This is the potential outcome when the treatment is not administered, which is zero point 0.4. Ideally, we need to know both. In the real world, we cannot know both. So I hope that answers your question.
तो लाइक खुद से फिर हम लाइक अज्यूम करते हैं ये वैल्यूज
नहीं, अभी
ये
बस I
वाली।
have given you some values. In actual, you can't
और
even assume them.
ठीक है।
Okay. So essentially, अगर आपने individual treatment effect find करना है or the individual causal effect, so that is just yi1 minus yi0, right? So I've written a very simple command to do that. I think everyone here should know how to do that in pandas. And then I have added that as a column called individual causal effect. Hence, I have the individual causal effects for all of these. I want to clarify one very important thing over here. जो causal effect होते हैं आपके पास और the treatment effect, it can be positive or it can be negative. Both have different implications. This is not something that's always positive. It's not correlation. So if it is positive, it means कि treatment का impact हुआ है more than like whatever was in the control group. If it is negative, it means that the treatment had an adverse impact on the outcome. With that, let's move on. And now we can calculate the mean of this particular column, thus giving us the exact average treatment effect value, which is 0.14. Now, in actual, we know that a lot of these values are not really visible to us. So we're going to try and compute the difference in means. And difference in means simply means that what I will do is I will go to those individuals that were given the treatment. Let me show you guys that as well. All right, df treatment t is equal to 1. And then I can just pass that Boolean array to my data frame. And this is what I have obtained. Similarly, these are the individuals to which the treatment was not administered. So, सबसे पहले I would want to separate these two groups out. Then, for the first group to which the treatment was administered, I can find the average of this particular value, the average of the outcome given that the treatment was administered, since we know that it was administered. Similarly, for the other group where the treatment was not administered, I can find the average of these particular values, which in a real world are visible to me. The outcome when the treatment is not given. And then I can take the difference of those two values, and that is my difference in means. And I have done precisely that over here. So I've separated it out into two groups. found the mean for each of those two columns for each group and then subtracted it, which gives me an answer of negative 0.13. So we don't know what the treatment was, but this kind of tells us like difference in mean से हमें ये पता चल रहा है कि ट्रीटमेंट का एडवर्स इफेक्ट है आउटकम के ऊपर. Although the average treatment effect tells us that the treatment does not have an adverse effect, it has a positive effect on the outcome. Hence, we know that ATE is generally not equal to D. There's one important thing written over here. This happens because association is not causation. Essentially, this happens because there are some confounding factors involved, and we're going to look at that in detail through a case study. So, I have one simple example, and then we're going to walk through a slightly more complex example. Let me revert to my next notebook. Okay. Let's move on. So, consider a doctor who administers two different treatments for patients with kidney stones depending on the size of the stones. So, treatment A is surgical and treatment B is simple pills. Naturally, she prefers surgeries for patients with more severe cases and larger stones. We're going to circle back to this actually. The following are the success rates of her treatments after a whole year. So, let's see. If we just observe this data, and using this data, you want to tell, okay, the doctor has a new patient who has kidney stones, and suppose hypothetically the patient does not know कि kidney stones का size क्या है. Intuitively, would you recommend treatment A to this patient or treatment B to this patient? There are two different answers to this. Actually already added them over here, but anyway. So if you observe it right over here, you will see that treatment A has performed better for small stones over here. Actually, sorry, treatment A has performed better for small stones as well as for large stones. 96% as opposed to 87% for small stones and 73% as opposed to 68% for larger stones. So individually, it tells us that treatment A performs better for small stones and for large stones. But when you combine these results, you see that treatment B gives us a performance of 82% when you ignore the size of the stones and just look at the rate of recovery, which is more than that of treatment A. This we have covered in class as well. If someone would like to intervene and tell me what the name of this paradox is. So, guys, that is the Simpson's paradox. This happens when the trend reverses upon combining individual groups of data. And why exactly does this happen? It really corresponds to the number. See, the thing is, the distribution across treatment A and treatment B across different stones is not exactly even. Right over here, I can see that only 87 people only 87 people with small stones were given treatment A and 270 people with small stones were given treatment B. On the other hand, most of the people with large stones, 263 in total, were given treatment A, and a smaller proportion of them were administered treatment B. What can we understand from here? I'm going to come back to this particular line. So the doctor administers the treatment depending on the size of the stones. It means the doctor is naturally preferring treatment B for smaller stones because treatment B is simple pills and prefers treatment A for larger stones. If I make a causal directed acyclic graph for this problem, this is what that would look like. You guys have an entire lecture on just causal directed acyclic graphs, I believe, as well. For now, causal DAG just tells you the relationship between different variables. Now, treatment, and then there's an arrow that goes from the treatment to the recovery, which is evident because that's what we're trying to observe as well. Treatment has an impact on recovery. At the same time, the size of the stones has an impact on recovery as well. Now, this is where the problem comes. This particular arrow, the size of the stones impacts the treatment as well. Hence, I can label the stone size as a confounding variable or as a confounder. Confounder is exactly this, something that impacts the treatment as well as the recovery. Hence, my results are not going to be authentic. I need to control for the confounder in order to find the true treatment effects. Are there any questions at this point? Okay, all right, moving on. So, anyway, we're going to condition on the confounder. And I have added a little part of slides over here because I want to show you this math through the same example as well. So you have the conditional estimated treatment effect for x equals 0. X equals 0 is like whatever your confounder is right now. But then you also multiply it with the probability of x being equal to 0. And the same thing you do with 1 as well. And thus you can find the average treatment effect. Let's look at this through an example. Let me just share my screen on OneNote with you guys. Is my screen visible now? Okay, all right. I hope this is a decent level of zoom. So let me show you how you do this probability math. When I talk about conditioning, it simply means I want to fix the possible values of my confounding variable. And we know that our confounding variable is size, and size can only have two values. A stone can either be small or it can be large. So I will control for both of those values in size and then find the rate of recovery for treatment A and the rate of recovery for treatment B individually. So let's try and do that. So you are going to find the probability of recovery given that the treatment is A. And I'm going to fix one more thing right now, the size, and that the size is small. And then you have to multiply it with the probability of the size being small. Then I have to consider my other case as well, which is when the size is large. So I'm just going to copy this exact same thing. This time fixing the value of size to large.
जब आप ऑलरेडी वो वाली ट्रीटमेंट ले रहे थे जिसमें साइज स्मॉल है, तो फिर सेपरेटली प्रोबेबिलिटी दैट एस इज इक्वल टू एस क्यों मल्टीप्लाई किया बाद में?
I'm sorry, could you come again?
जब ओरिजिनल जो प्रोबेबिलिटी है कि ट्रीटमेंट ए गिवन के एस स्मॉल है, तो ऑलरेडी अगर स्मॉल की प्रोबेबिलिटी ले रहे हैं तो अलग से प्रोबेबिलिटी ऑफ बीइंग स्मॉल क्यों मल्टीप्लाई कर रहे हैं आप?
Oh, no, no, this is your rule in probability. You have to do that. Let me add some more math over here, then let's revisit this. I'm going to start with just this particular value. What is the probability of recovery? Given that the treatment is A, I'm going to come to this column and that the size is small. So this rate is 96%, 0.96. And then we're going to multiply it with the probability that the size is small. So let's look at this. In total, how many stones are we concerned with? There are 350 stones over here, and there are 350 over here. 350 patients, I mean. So I'm going to do 350 plus 350 in my denominator. Now I want to know how many of these patients had small stones. So these are my numbers, 87 and 270. These two numbers are for the patients with larger stones. So I will do 87 plus 270. And then I want to do the same thing over here as well. Now, the probability of recovery, given that the treatment is A and that the size of stones is large, is right over here as 73%. And then you would want to multiply that with 1 minus this thing, basically. Or in this case, 263 plus 80 by 700. I don't remember the exact answer to this, so let me just quickly calculate and add this over here. So this gives you 84.7% or 0.847. And then you can do the exact same thing for the treatment B in as well. So I'm going to add that right over here. You're going to change some things here. This remains the same. This value will change and this will change. So let's see how that works. Now the treatment is B. You first fix the stone size to small and then you fix the stone size to large. All right, let's look at this particular probability. The rate of recovery, given that the treatment is B and that the size is small. So this is where the treatment is B. This is where the size is small. That is 87%. Over here, we want to look at the rate of recovery when the size is large, which is 68%. Let me quickly compute and add these values as well. So this gives you 77.7% approximately. And the values that we have found now essentially take into context the number of people that are distributed against each category as well by conditioning on size. Now we can make an informed decision and say that in spite of the size, 84 treatment A has an 84.7% recovery rate and treatment B has a 77.7% recovery rate. Hence, if the doctor does not know the size of stones for a given patient, they can naturally recommend treatment A. Are there any questions at this point before we move to our case study? All right, I'm going to add the solution over here. Moving on to, I think this notebook should be available to you guys already, but I have made some slight adjustments, so I will probably add it on LMS again. We have a very interesting data generating process over here, which I'm not going to walk you guys through right now. We will circle back to it, however. For now, let's look at what we are generating the data for. We're going to try and understand Simpson's paradox through a more complex example. Let's see, maybe I can zoom in a little more. Okay, all right. So here's the context. The world is confronted with a rare disease for which different public health agencies are trying to work and find new solutions. So suppose that you have to conduct an experiment as a data scientist. Actually, you don't have to conduct an experiment, you're already given the data. You have to find evidence for the effectiveness of the drug. You're trying to determine if the given drug for this new disease is effective or not. You don't have time to run an entire clinical study. A clinical study would involve an experiment where you take a bunch of people with or without the disease, you put people in different categories, you randomly assign them to the treatment group, to the control group, and then you administer the treatment, and you don't administer the treatment in control group, and then you look at your data. But a randomized control trial is infeasible right now, so you already have the data set for a given country. Using that data, you're going to try and determine if this drug is effective or not. We have three variables in our data set. Let's go over each of them. Z represents the severity of symptoms. Z can only have three values. If the symptoms for a given patient are mild, then Z is 0. If they're strong, it's 1. And if they're critical, then it's 2. Then A represents the treatment. It's basically the same thing as capital T. If the patients are assigned to the treatment group, which means they are treated, then A is 1, otherwise it is 0. Y represents the outcome. In this case, the outcome is binary, survival after 1 month. Either after 1 month, the patient was found dead or alive. With that, let's look at our data set. This is what we have. Using our data generating process, which I will circle back to, we have generated 10,000 rows across these three variables where you have Z, A, and T. I can quickly show you the unique value counts for each as well to show you that the distribution remains roughly the same. All right, so roughly I have around 3,300 people across each case of severity of symptoms. Roughly, I have around 5,000 people in each of the two groups, treatment and control. And roughly, I have around 5,000 positive outcomes, the people being dead, sorry, alive, and 5,000 negative outcomes where the patients died. All right, with that, let's move on. It feels like our data seems pretty evenly distributed. So let's see. Now you want to measure the average treatment effect. That is the chances of survival if someone takes versus does not take the treatment. You decide to estimate the following quantity, and I think we all know that the following quantity is simply the difference in means estimator. This time, we are looking at a real world scenario. If a person was given a treatment, we know that the value of y is either 1 or 0. Either the patient survived or they did not survive. We have no idea what would have happened to that patient if the treatment was not administered. And it works vice versa as well. So that is what a real world scenario will look like. Let's see, we have a graph over here. So let's go over this. On the x-axis, you have the treatment for which we only have two values. It's red where the treatment was not administered, that is your control group, and it's 1 where the treatment was administered, that is your treatment group. On the y-axis, you have the rate of survival, which has just been distributed across both these groups. So for group 0, this number right over here, which I think is approximately 55%, approximately. So this number right over here tells me the percentage of people in group 0 that survived. Similarly, my blue bar ends roughly at 50%, which tells me the percentage of people that were administered the treatment and survived. Are there any questions as far as this graph is concerned or up until now? Okay, all right. So using these two, I can compute the difference in means. estimator. So this is what I've obtained for the estimated average treatment effect. Negative 0.11, and a negative causal effect tells me what? It tells me that the treatment has an adverse effect on the outcome. It basically it means that if people were given this drug, they were more likely to die. Now, I cannot report these findings, and there is something wrong with this over here. Anyway, let's see. So it looks like the treatment has a detrimental effect on survival, which suggests that it is not effective. Soon we will realize that this is not true because we were told that this is a state of the art treatment and that it should be effective. So let's see. Right now, we did not take into account at all the severity of symptoms for any given patient. We just looked at whether the patient was given the treatment or not and whether they survived or not. So let's take the other into account as well. By the way, these are your simple pandas commands. I have located just all those indexes where my where the value of A was 1, the people were in the treatment group. This is another way to index Y, which is the outcome. And then I found its mean. Similarly, I took the mean of the control group and subtracted it from it. And I've stored it in a dictionary. Later, we will be appending more to this dictionary. Anyway, let's see. Now I'm going to find the conditioned average treatment effect across three different classes of symptoms. Either my symptoms are mild or they're strong or they're critical. So let's see what I have done over here. Let's look at just this particular piece of code. What does it give me? So first I have found the indexes of all the people that were given the treatment such that their symptoms were only mild. And then I have, of course, found the average of Y. Similarly, I have found the average of the people that were not administered the treatment and had mild symptoms. And then I've done the same thing for strong and critical symptoms as well. And these are the values that I have obtained for. Basically, it's still the difference in means, but this is conditioned on the category. Now I know for each category of symptoms. And when you look at these values, I'm going to show you a graph of these values as well. This is what we have obtained. What can we conclude from this given graph? I will give you guys a few seconds to process and think about this. You're welcome to respond, but I'm going to put a pause anyway. All right, would anyone like to comment on the observations from this graph? Okay, anyway, there are two important things that we can observe from this. Firstly, all the values of conditional average treatment effect are positive. It means that across all three categories, the treatment has had a good impact on the outcome. The treatment has been effective, even though when we did this above, ignoring all three values, we found that, see, the bar in blue is shorter than the bar in red. We found the estimated average treatment effect to be negative. So, across all three categories, we found that the treatment has a bad effect on the outcome. Across each individual category, we see that the treatment has a positive effect on the outcome. That's our first observation. The second observation is that for people with stronger symptoms, as opposed to mild or critical symptoms, the treatment has been most effective. You can go through this on your own later. We've already been through it. All right. However,
मेरा एक
yeah,
क्वेश्चन था ऊपर वाले
yes,
से.
go on.
हमने पिछले वाले एग्जांपल्स के अंदर इधर हमारा जो कंफाउंडिंग वेरिएबल है वो इधर सेवेरिटी ऑफ सिम्टम्स होगा ना। तो जो
Absolutely, yes.
जो पिछली एग्जांपल थी उसके अंदर हमने तो डिफरेंट कंफाउंडिंग वेरिएबल्स को फिक्स करके आपस में प्रोबेबिलिटीज ऐड की थी। तो इधर में सब्ट्रैक्ट क्यों किया हमने इधर?
अच्छा, आपने probabilities अभी compute नहीं की. The thing is, in the previous example, we computed the probabilities. We did not compute the treatment effect. हम treatment effect इसीलिए नहीं compute कर सकते थे because we were already given the combined data in yes or no format. We were already given it as percentages. So you could not do that. This is a different case. However, this is your
अच्छा,
confounding variable. We're going to explore this a little deeper. Are there any other questions? Okay, all right. Anyway, moving on. So I think that this is very puzzling. If individually, if like across all three categories, your treatment has a bad effect on your outcome, then how is it possible that across each individual category, uska acha impact hai aapke outcome ke upar? So let's do a little more analysis. Let's see, what have I plotted over here? The probability of receiving the drug with respect to the symptoms. Look at your x-axis. X-axis covers the three categories of symptoms: mild, strong, or critical. And then look at the y-axis. Y-axis covers y-axis covers the value of A, and A just tells us the group to which people were assigned. All right, and we've converted those values to probability. So for the mild group, if you look at this, it tells us that less than 10% of the people with mild symptoms were given the treatment. You know, the value of A was 1 for less than 10% of the people with mild symptoms. For strong symptoms, this value is higher, roughly 50%. So, roughly 50% of the people with strong symptoms were given the treatment. The other 50% were not given this treatment. And then for critical, almost like around 90% of the people were administered the treatment and 10% were not. What can we conclude from this? I will again give you guys a few seconds to think about it. Would someone like to comment on this? All right, anyway, from this we can conclude that the severity of symptoms has an impact on A. I will repeat myself. Given the severity of symptoms of a patient, this is what the doctors in that country used to determine whether they should even be given the treatment or not. This is how we know that Z is a confounding variable when we are trying to directly observe the impact of A on T. Sorry, A on Y. Y is your outcome. We cannot directly observe the impact of the treatment on your outcome when we have such a distribution that the severity of symptoms impacts both the outcome and the choice of treatment. It is a confounding variable. We have lots of people with critical symptoms that have been given the drug, but we have very few people with mild symptoms that were given the same drug. This is the same as, let me just give another example over here. Dr. Mubin's example from one of your sessions. If you're trying to determine the impact of smoking on lung cancer, and suppose you have two different groups of people such that there are systematic differences between the two groups. Suppose people in one group are generally people who exercise more. These are non smokers. And people in the other group include people that do not exercise very frequently. Then maybe our results will tell us that the average effect or like the likelihood of developing lung cancer for the people who do not smoke is less than the likelihood of people developing cancer given that they smoke. In actual There is a systematic difference. We don't know whether the result that we are observing are because like people were exercising more in the other group, or whether it is because they were smoking. This is essentially what happens. Similarly, in this case, we cannot determine that the given result being whether people died or they survived this disease, we don't know if that happened because their symptoms were severe or that happened because they were given this treatment. Are there any questions at this point? Okay, all right, moving on. So the probability of being treated increases with the strength of symptoms. All right, moving on. Next, we are going to observe the relationship between the probability of survival with respect to symptoms. So now we've looked at symptoms. We've looked at the relationship between symptoms and the treatment administered. And we know that there is a relationship between those two. People with more severe symptoms are more likely to be given the treatment. Now we're trying to observe the probability of survival with respect to symptoms. And again, I will give you guys a few seconds to process this and think of what we can determine from this given visualization.
आई गेस ये कंफर्म नहीं है कि जो माइल्ड पेशेंट सर्वाइव ज़्यादा इसलिए करें क्योंकि उनको ट्रीटमेंट कम दी जा रही है या उनके सिम्टम्स इटसेल्फ माइल्ड है.
All right, but what can we determine like exactly is he graph से without everything else that we've looked at? Just like looking at this graph, इस graph से हमें क्या पता चलता है?
लेस सिवियर द सिम्टम उतना सर्वाइवल रेट ज़्यादा है.
Perfect. That's exactly what I was looking for. So this helps us determine the relationship between the probability of survival and the symptoms. And we can very clearly observe कि जितने less severe हैं symptoms, उतने ज़्यादा chances हैं that the person will survive. So this is a pretty different relationship, the exact opposite from what we observed over here. But I think we have successfully established कि जो आपकी वैल्यू है z की the severity of symptoms उसका impact survival के ऊपर भी है and उसका impact treatment choice के ऊपर भी है. All right, let's see. The probability of survival clearly decreases with the intensity of symptoms. So let's look at a graphical representation. And this is the exact same causal graph that we observed for our previous example as well. See, A impacts Y, but Z impacts both A and Y. So essentially, in a causal directed acyclic graph, eventually what you do is when you're trying to determine the impact of one variable on another, you generally start by listing down all the paths between those two variables. Now, between A and Y, I have two paths. Let me see. Acha, ye listed hai aapki paths. So this is the direct path that goes from A to Y, and then there is this other path. By the way, we can ignore directions right now. It is still a valid path that connects A and Y. All right. And essentially, in the first path, z is a confounder. We need to fix the value of z somehow. We need to control for z. We need to intervene in order to observe just the relationship between a and y. So this is a very important piece of information. These two given paths tell us that the impact that we observed directly when we computed, let me just clarify किस computation की बात हो रही है, this one. When we computed the difference in means to estimate the average treatment effect, so उसमें basically इस path का impact था. Circling back to this, yeah. So that could have been due to any of these paths. In this case, I actually know that it's because of Z. All right. So to get this answer, we're going to isolate the A goes to Y path and then reveal the true causal effect. And this is a very interesting phenomena. I'm going to quickly circle back over here. This is what we determined, that the difference in means is not the same as ATE. Why? Because association is not causation. In more detail, why? Because there are often confounding factors involved, some that we know of and some that we often not know of, and that essentially biases our results. That is what happens. Hmm. And when exactly is D equal to ATE? You looked at a very detailed mathematical proof for this in, I believe, lecture 11 here. But can someone tell me in very simple words, without the proof, when is the difference in means equal to the average treatment effect? What do we need to do to ensure that these two are equal? Because obviously we cannot determine the exact average treatment effect. So I'm going to pause for a few seconds over here. So guys, the would someone like to answer, by the way? No. So D is equal to AT even there are no other systematic differences involved between your treatment and your control group. Let's simplify this further. If I randomly assign people to treatment and control groups, then I determine the difference in means. I can say that it must be a very good estimate of the average treatment effect. In even simpler words, it means कि जो आपकी selection हुई है treatment की, that should not depend on any other factors. That selection should be absolutely random. Right now, through this particular graph, we observed that the selection of treatment is not random. This process needs to be randomized. If this process was random, and people were placed in any group with like the same probability, if like you have a given person, suppose, and आपने उन्हें smokers या non-smokers के group में डाला है, then the possibility of putting a person in each of those groups should be 50% each. Kind of like tossing a coin. You don't look at their symptoms, you don't look at anything else. In our cigarette example, you don't look at whether the person exercises regularly or not. You don't look at the gender of the person. You don't look at anything else. You just take a person, you flip a coin. For instance, it lands on head, you put them in the treatment group. It lands on tails, you put them in the control group. Essentially, for this, we're going to do the same. See, if I had a way to cut this particular path that goes from Z till A, I have solved my problem. Now the only path between A and Y is the direct one that goes from A to Y. There are no confounders whatsoever in this path. Let's see how we can do this. See, there are two ways of going about this. In the previous example, we looked at our already collected results and then we computed individual probabilities for each group by taking into account the size of both groups. In this case, let's see how we can modify our data generating process to achieve the same results, to achieve a better estimate of the average treatment effect. And now I am going to take you back to the data generating process, which I said we would circle back to. There are lots of functions here that you can go through on your own later. Essentially, this is the function that I am concerned with, generate data. Let's see what's happening over here. Z is a random integer between 0 and 3, which means that Z can either be 0, 1, or 2. And we already know that because like 0, 1, and 2 correspond to mild, severe, and yeah, mild, strong, and severe symptoms. And then policy, let's see what I have over here. I have an array with values 0.05, zero point 0.5, and zero point 0.9. This array represents the probability of treatment for each z. Let me clarify this over here. These are the values of z that it corresponds to. This is something that I have set myself. ये value मैंने खुद set की है. So I've essentially already told my data generating algorithm that if z is equal to 0, if the symptoms are mild, then the probability of giving the treatment should be 5%. If the symptoms are strong, then the probability of giving the treatment should be 50%. And if the symptoms are severe, then the probability of administering the treatment should be 90%. And thus I have generated I have shown you guys this function in NumPy in, I think, one of our beginning tutorials, tutorial 2. So numpy.array, and then this is your function that generates a random number. And I have given a condition that the random number should be less than or equal to the probability of generating z for a given c in this array. Essentially, what I'm going to do over here is I am going to generate my values of a randomly, but in such a way that it follows these probabilities. With that, let's look at the next thing that we are generating in our data. All right, so next we have the survival. And survival is either 1 or it is 0. I have two distinct arrays over here. Let's look at each of them. The first array represents the value of survival as 0. The second array represents the value of survival as 1. Now let's see what exactly happens. I have three values in each array because I'm trying to establish a dependency between the value of z and the survival. Let me further elaborate on this. If the value of z is 0, then the survival being, or like the value of a being 0, should be with, then a will be 0 with the probability of 75%. And there's only a 25% chance that, oh, I said it the other way around. My bad. And there's only a 25% chance that the person will not survive. And then I have done the same for the value of survival, for the value of Z as 1 and 2 as well, for both my treated and untreated groups. So let's see over here. Yeah, let me clarify. There is a 75% chance of the value of survival being 0 if the value of z is 0. There is a 95% chance of the value of survival being 1 if the value of z is 0. All right, and with that, I have used my function to generate an array y as well. Then I have called this function in such a manner that I generated 10,000 rows of data. And my 10,000 rows have been generated in exactly a format that follows this trend. What can I modify over here to ensure that, basically, to ensure that Z does not impact the choice of my treatment? Z should not impact A. How can I modify this function to ensure that Z has no impact on A? Like, जो मर्जी symptoms हो patient के, they have the same chances of ending up in the treatment or in the control group. I will leave this piece of code open and give you guys a few seconds to actually think about it.
प्रोबेबिलिटी ऑफ ट्रीटमेंट बराबर कर दें सबके लिए.
Absolutely. The question is कि आप उसको policy में modify करेंगे या survival में modify करेंगे?
आई गेस पॉलिसी में करेंगे क्योंकि सर्वाइवल रियल वर्ल्ड सिनेरियो में तो नहीं आप कंट्रोल कर सकते, तो
Absolutely.
पॉलिसी को ही कर
Perfect.
सकते हैं.
Perfect. That's exactly what I was looking for. अगर ये सारी probabilities 50% हो जाएं, तो मैंने जो नीचे trend देखा था, and let me tell you guys, this is the trend that I was talking about. I will not observe this anymore. I observed this trend literally because I had set those probabilities when generating my data. If I set all of these probabilities to 50%, see, this is my next data generating algorithm. Essentially, this is the only thing that has been modified. After this, let's generate our same graph again. The probability of receiving the drug with respect to the symptoms. So again, I have Z on my x-axis, where Z can either be mild, strong, or critical. And then on the y-axis, I have the probability of the person being assigned to the treatment group. And now they're all 50%. Essentially, जो ये एरो था between Z and A, हमने उसको खत्म कर दिया, and now we're just tossing a coin and randomly placing people in each group. This is what you need to do to ensure that difference in means gives you a good estimate of the average treatment effect, or that it is equal to the average treatment effect. Let's go over this. I don't think you guys have covered the do operator in class yet, so I'm going to cover this to a certain depth only right now. But essentially, this is what I'm computing. And I think it's exactly what you were computing over here as well. Operator is the only difference now. Yeah. So this is the formula for when you are computing the difference in means, right? So it's the probability of the estimated of whatever the mean is for the treatment group minus the mean of for the control group. And that's exactly what we have over here as well, except that where I have a equals 0 and a equals 1 given, so ये given that a equals 1 है and given that a equals 0, now I have set a to 0 and set a to 1. Let me circle back to that. So precisely this is what I have over here. This do is the only thing that is different. The do operator tells you that you are intervening, you are manually setting this value to 0 or to 1. And I'm going to go over this again towards the end as well. For now, let's look at our next graph now. Now, again, you have on the x-axis the treatment. Either the person is assigned to the control group or to the treatment group. On the y-axis, you have the probability of survival. So the percentage of people who survived when A was equal to 0, that means the percentage of people surviving who did not get the treatment is just under 40%. The percentage of people that survived in the treatment group where A equals 1 is over 60%, I think close to 70 actually. And now if I use these values to again compute in exactly the same manner, by the way, now you have the exact same equation for difference in means as we were using before. Now when I use that to compute difference in means, it gives me 0.27. Let me remind you all very quickly that previously we had negative 0.11, which intuitively showed us that the treatment has an adverse effect on the outcome. If you're going to give the person this drug, they're more likely to die from this disease. Now we have realized that if you're going to administer the drug to a given patient, they have better chances of survival. The value is positive now. This is the ATE for randomization. And that is why I stored it in a dictionary to clarify, so that I have it initially and then I have it when I introduced randomization.
मेरा एक क्वेश्चन था वो ओरिजिनल
Yes.
पॉलिसी वाला डेटा जनरेशन से आपने हालांकि लाइक पॉलिसी तो इक्वल कर दी प्रोबेबिलिटी, लेकिन डेटा जनरेशन में आपने फिर भी लाइक स्पेसिफाई किया हुआ था कि अगर ज़ीरो है और ट्रीटमेंट गिवन है तो उसकी सर्वाइवल रेट डिफरेंट होगा सिम्टम्स के
Oh,
लिए
no, no.
से
Survival rate. Oh, hold on. Let me clarify. Hold on. So let's look at this causal directed acyclic graph. इसमें A का impact है on my outcome. So treatment का impact है on the outcome. And then जो आपका severity of symptoms वाला variable है, which is Z, उसका भी impact है on the outcome, as well as on the, it also has an impact on the choice of the treatment that you're administering to the given
वो तो
patient.
आपने बस ये वाला एरो तोड़ दिया
Yes,
सीज टू ए वाला
exactly. आपने जो arrow break करना है, that has to be exactly this one, the one that goes from Z till A. We're not breaking this other arrow. Abhi, I have written my code for the data generating process in such a manner that I want to ensure these correlations. All right?
अच्छा ऑल्सो असूलन जी और वाई के दरमियान भी हमें नहीं तोड़ना चाहिए अगर हमने सोली ए और वाई का हमने इफेक्ट देखना है
Nice.
उनको
See,
फिक्स
that doesn't matter. Let me circle back to our previous example. If you're trying to determine the, yes, please. So if you're trying to determine the impact of smoking on the probability of a person developing lung cancer, right? ये हमारी एक previous example है. In this case, if you have two groups, the treatment group and the control group, treatment group में people are smoking, control group में people are not smoking. And then let's suppose there is another variable which is a confounding variable, exercise, like I was saying. So essentially, it would mean if people are, when I say that exercise is a confounding variable, I mean to say that it impacts both the choice of treatment and it impacts the outcome. So obviously exercise का impact outcome के ऊपर तो है. Exercise has an impact on the probability of, in this case, I don't know for sure. So let's suppose we know that exercise does have an impact on the probability, on the chances of developing lung cancer. If a person is working out, they're remaining healthy, maybe they're less likely to develop lung cancer. So that arrow stays in place. But what I'm saying is that exercise का impact है on whether people smoke or not as well. ये connection break करना important है. This is going to give me a spurious correlation. This is going to confound my results. If I And that essentially just means कि जो treatment group है, for instance, उसमें there are fewer people that exercise, and जो control group है उसमें there are many more people that exercise. So I need to break that connection. I cannot break the connection between exercise being linked to a better health. I hope that makes sense.
और जो पिछला एग्जांपल था जो स्टोन्स वाला था उसमें आपने ये कनेक्शन ब्रेक करने के लिए वो प्रोबेबिलिटी वाला फॉर्मूला लगाया था.
Exactly. उसमें मैंने probability calculate की थी after conditioning on what I already had, which is what you do. This is an alternate way where I'm showing you how changing the data generating process to ensure that you're flipping coins, there is randomization. I'm showing you how that gives you a better estimate of ATE. In a real world, this basically means कि एक randomized control trial ही हो रहा है, which is not always possible. So you should know how to do that probability math.
तो बेसिकली हमने ए और जी के दरमियान कनेक्शन तोड़ दिया, लेकिन
Yes.
डिपेंडिंग ऑन कितने माइल्ड वाले या कितने स्ट्रॉन्ग वाले ट्रीटमेंट या विदाउट ट्रीटमेंट वाले ग्रुप में आते हैं तो वो आपके रिजल्ट्स को स्क्यू नहीं कर सकते टुवर्ड्स अ स्पेसिफिक साइड.
Could you elaborate on that?
मतलब
Like
कि
आपके results को क्यों skew करेंगे?
कोइंसिडेंटली अगर ट्रीटमेंट ए वाले ग्रुप के अंदर जिसको ट्रीटमेंट दी है उसके अंदर स्ट्रॉन्ग सिम्टम्स स्ट्रॉन्ग सिवियरिटी वाले ज्यादा लोग आ गए और वाई वाले के अंदर कम लोग आ गए तो
Okay, no, no, that
उससे
doesn't matter to us. See, the thing is, we cannot break that connection. उसका हम कुछ नहीं कर सकते. Like, obviously, I can modify the values in probability to do that, but in a real world, that is impossible. कि अगर severity of symptoms का impact है on the rate of survival, so there is nothing you can really do about that, right? You can just make sure कि severity of symptoms का impact treatment के ऊपर मत हो. In that case, your results will be biased. In this case, your results are not biased. That's why we always make a causal directed acyclic graph, because using the graph we can see कि treatment और effect के बीच में सिर्फ एक ही path है, and there are no confounding variables on that path.
तो बेसिकली फिर वो एक रैंडमाइज्ड एलिमेंट हो गया तो बैलेंस आउट हो जाते हैं कि
Exactly.
रैंडमली
Yeah,
सिस्टम है.
precisely. So
और
बाकी और भी बहुत elements होंगे जिनका treatment पे impact हो सकता है. Maybe women are more likely to recover from this disease. Maybe young people are more likely to recover from this disease, and all of those could be impacting by. लेकिन when they are impacting the treatment, तब basically हमारा काम खराब होता है.
अच्छा ठीक है वो अब क्लियर होगी बात.
Okay, all
थैंक यू.
right, perfect. No worries. Okay, all right. I think that will be all actually. I'm going to circle quickly back to the do operator and tell you guys the difference between conditioning and intervening. So conditioning means जब आपने जो आपके पास data given था, for instance, in our initial जब हम इसमें पहला case देख रहे थे where the data generating process was biased, where your symptoms की severity was affecting the choice of treatment as well. In that case, you were just conditioning. आप condition कर रहे थे अपने symptoms की value को, और हर symptom के against you were determining जो भी उसका conditional average treatment effect था. In case of intervention, you manually set the value of a variable to something. So जब हमने manually set किया उसकी value को, that is essentially just when we were setting the probabilities to 50%. So at that point we intervened and we determined कि अब हमने randomly इनको ये values assign करनी है. We are not going to use those initial values. And this will be covered in more depth further on as well. For now, are there any questions before we wrap up this session?
जब आपने पॉलिसी को 50-50 किया, तो जो आपकी कंडीशनल वाली प्रोबेबिलिटी जिसके अंदर आप वेरिएबल्स को फिक्स करके सर्वाइवल रेट निकाल रहे थे, उसपे भी फ़र्क पड़ेगा?
See, that's exactly what we computed. वही हमने compute की थी. That's exactly what changed. सिर्फ उसकी notation में difference था. You would have observed कि I wrote down, given that do A equals 1 and do A equals 0. Yeah, whatever that was. Yeah, it was do A equals 1 and A equals 0. Like in actual, my math was exactly the same as that when you do it for given A equals 0 and given A equals 1. So your math didn't change, but we did an intervention over here.
अ, अच्छा,